previous sections. That is the databases for sequence, protein DNA structure. So I'm going to start by going back to the drug bank. Mm-hmm. Now, here the easiest example to work with will be paracetamol or even Tylenol. And more than that, there's other pieces of information that you can work with, and it's, for example, the targets. If you already know an important protein for a disease, you can look it up. Looking up, for example, well, even hemoglobin. Hemoglobin is not as exciting as a target because pretty much drugs have been created to deliver iron for any deficiency, or the related one, Plasmodium falciparum, which can be attacked to a drug that seemingly targets hemoglobin beta. So those are not really exciting targets, but most of the actual exciting targets are gonna be actually antivirals, antibodies, and in some cases proteins or peptides such as insulin. So in a way, for the purpose of this class, this database is limited, but there's one that it's actually fairly important and fairly useful, and that is what I want to start covering in during this class and the next one. We already took a very quick tour through it, and we know that if we look, for example, for Tylenol, we get a plethora of information from the formulation, the different names, and if we open this, wow, contrast is terrible, at least from here. If we open this tab, we can get access to information such as the economics, clinical trials, and for today, what I want to focus is on properties. You heard right. Properties. Here, these properties, some are, well, there's two big divisions here. One is the so-called experimental. What does that mean? In general, and we gotta be careful even to their sources, it means that those have been measured. That is, somebody actually tried to melt this. Have you performed these experiments in chemistry lab, or any of those? No? Not yet. Well, they are not that hard. What is actually difficult for those experiments is to get enough of the compound that you need. Depending on the equipment, you might need grams, which is trivial for some substances, but not for everyone. Solubility, that's another type of experiment. Log P, log S, and pKa. And you, for sure, at least should be able to recognize pKa. That is the equilibrium between the acid and the conjugated base as expressed in water at a given concentration. The pKa of this molecule of Tylenol is 9.38, which means that pretty much for any biological purpose, it's gonna be in the protonated state, right? Do I have to recap that from biochemistry, or do you still remember how it works? So that I want to take that as a no. The pKa can be viewed in the simplest fashion as the midpoint where half of your compound is protonated or deprotonated. If I go back, in the structure way over here to the beginning of the section and click on the structure, what I get to see is pretty clear. We have a nitrogen, we have an oxygen, and an alcohol. This will be like a carbonyl. And what is likely to lose or gain a proton is the nitrogen, right? As a base, the pKa should be on the basic side of the pH scale. So what the pKa tells us is that we need to be at a pH about 9 for this nitrogen to lose that proton. Under that pKa, this is the structure. Above the pKa, it's gonna lose the structure, the proton, and gonna gain a charge, right? It's not as easy to imagine that for every single compound because under different circumstances, that nitrogen is not the only oxygen, is not the only nitrogen that can lose or gain protons, right? Anyone could actually gain them, and some reactions will break the benzene group and give you something with a double bonded oxygen and so forth. And in fact, that is a very important difficulty for chemistry in general. Okay, so back to the properties. What is log P? Log P is a equation, it's a constant similar to the pKa because it uses logarithms, and it relates if you place this substance in an water, another organic solvent interface like octane, how much of this compound is gonna prefer to stay in water versus staying in octane, right? The more soluble in water, the less soluble in octane. And any value of log P that is positive means that the molecule prefers to be in the organic solvent, in octane or octanol. It varies in different experiments. If this log P was a negative number, it will prefer to be in water. Okay? So positive, it's hydrophobic. It could be considered a hydrophobicity scale. If log P is positive, it's more hydrophobic. If log P is negative, it's more hydrophilic. Because it's a logarithm, every unit that increases in the log P, it's an order of magnitude. So log P0 means it's equally soluble in water and organic solvent. Log P1 means it's 10 times more soluble in the organic solvent. Log P2, it's 100 times, and so on. And the same for the negative value. Log S, it's a similar equation, slightly more complex, but this one takes into account the fact that this molecule can be protonated or deprotonated. This is something that maybe we should start teaching in biochemistry, because through that equation you can actually show that if a compound is charged, it's always going to be more soluble in water. Whereas if it's neutral, it's always going to be more soluble, or, well, you cannot tell the preference, but it's likely to be more soluble in an organic solvent on the hydrophobic environment. So according to those brief explanations, according to this log P, if we were considering only the protonated, the neutral state, it's more soluble in organic solvent. But if we were to take into account a version of this molecule that is charged, it's going to be more soluble in water. And this is supposed to be experimental. Ideally, we should have to check these references to make sure it's actually an experiment, right? Not a reference value or something like that that hasn't actually been measured. Down here, in the same page, you can see that we have the same values, but as predicted properties. Now, it's not going to be obvious the reason for that. You could ask me, and you should, why are those values experimental and predicted? Well, because for drug design and other applications, you want to work with thousands of molecules. So if you were to measure those experimental values 1,000 times, it's going to be actually time-consuming and expensive. So many sources, many programmers, many chemists have been trying to come up with ways to predict these values. Here, for example, we see two different log P's predicted by this source and by this other program. And if you notice, ChemAction is the manufacturer of Sketch, the program for chemistry that we have shown. And the log P, it's not exactly the experimental one, but it's close enough. Following the logic of a logarithmic scale, this one and these two are in the same order of magnitude, right? It's like comparing between 4, 5, and 9, actually. It might be off, but it's not that wrong that it's going to be bad or useless. Then we have the log S, which according to this experimental value, it's a little bit more exaggerated. it's going to be slightly more soluble according to this prediction. Here is the pKa of the nitrogen again, and a couple of values that are important for drug design and some other calculations, such as physiological charge. Who understands what that means just by reading physiological charge?
What's the charge inside the body?
Yes, but what does that mean inside the body? In terms of pH, for example, as the pKa would predict, right? What pH is inside the body? That's in the bloodstream. 7.4 to 7.2 to 7.6. What about the stomach?
Just 2.
1, 2. For if this physiological refers actually to pH neutral, 7, it's accurate. And for the case of this basic compound, even at pH 1, it's going to be still the same, right? Because this is not an acid, it's a base. The hydrogen acceptors, donors, polar area, and other properties down here are important for drug design. And here, for example, is a name that you might see if you are more interested in drug design, the rule of 5. That rule of 5, briefly, is a set of 5 physicochemical properties that will define a good drug. If any of those values is exceeded or not met, the drug is unlikely to be useful. And as you can imagine, some are very obvious, like the molecule cannot be too big, or it cannot be too hydrophobic, and others are less obvious, such as the hydrogen bond counts or donors. How will that affect? It's not as obvious to see, but that can be predicted. Now, I'm going to go back to the top, to the structure. Okay, and keeping this on this side of the screen, what I'm going to do is now open Sketch, and please do the same. I'm going to try to set it in such a way that we can see the molecule from the website and the window for the Smarvin sketch. And I brought a mouse so I can click exactly as you click. Usually I don't use a mouse, but I think that for this purpose of the class it's important. I'm going to steal this chair because standing next to the table is kind of uncomfortable. But as I showed you, we can use this program to do either one of these two things. We could just copy the compound, right? And it's going to be pretty easy because it's a simple one. But if we were very, very lazy, we can go to structure and to name to structure. That should bring up a window, kind of like this. And there we can type Tylenol and click import. Structure, name to structure. And unless we did something terribly wrong, there we go. Does it look like exactly the same? Yeah, but that's a rotation of a single bond. That doesn't matter. Now, what it's going to be very useful about this program, now that we have this representation, is that we can use the calculations. And these calculations, as you saw in DrugBank, are going to be or should reproduce those calculated values. So if we didn't know that this was Tylenol or this molecule was not represented in DrugBank, we could go here and actually click on the log P and estimate that log P. So go to calculations, partitioning, and click on log P. It's going to open a window such as the one that you can see on the screen. Don't change anything. Most of the parameters are okay as they are. Click OK. And if you get this error, just click OK. And we should get a window like that. Did you get it? The program at this point is friendly, but not so friendly that we know exactly what happened. But let me explain to you. Chemically speaking, a molecule should be neutral, and the charge can be distributed among the atoms. And here you can see an oxygen that, according to biochemistry, should be polarized and have a relative charge. In this case, it has a positive charge of 0.0, but this one has a negative charge of 0.14. Those relative charges are assigned based on experiments, quantum mechanics calculations, and other properties, and they just have to add up to 0 for the whole molecule. And over here we see the surface, the solvent accessible surface area, that also is taken into account in these calculations. In a way, you have already worked with this. You know that atoms have a different size, a different van der Waals radius, different masses. That is taken into account there. And the calculation, it's on top. The log P, according to Chemaxon, should be 0.91. Is that similar to the one in the page?
I don't know.
And how will you find out, Rodolfo?
In properties.
You just go back to the page. Oh, I went way.
Name to structure.
No.
You go again to properties, and the log P as calculated by Chemaxon in the website is exactly the same as calculated by Chemaxon on your desktop.
Ah, yes.
Mhm.
Es que había dos log P.
Yeah, the other one was calculated by another program, A log something, right?
Ah, no.
Yeah, you know.
A log
Okay.
GPS.
Okay.
A log, yeah, A log PS, which is just another algorithm. Now, how will we calculate a log? Oh, well, sorry, my program crashed. If you close those windows and your program doesn't crash, you should have the window with the Tylenol again. I don't, so I have to go back there. How will we calculate the equivalent for the log S or the log P? I mean the log D, the one that takes into account the charged molecule.
The same. I don't know.
If we try the calculation for partitioning a log D, which will be an equivalent for log S, what we should usually get is, oh, sorry, no, that's not the one.
Log D.
Yeah, no, let me show you a little trick.
Apenas lo está.
I'm gonna change the charge of the nitrogen, so I have to click on it, go to atom, and quite simply and literally change the charge. And set it to +1, right? That would be a protonated nitrogen. So go to atom, charge, and select +1.
Esa, NH2. Yeah.
Okay, and now if we repeat the calculation partitioning and log P, and go to the OK and the error window. Oh, what happened here? Oh no, we got the other error.
Creo que tiene selección. Creo que es como es-
Yeah, because of the selection, it's not letting me do it. Thank you.
Gracias.
Did it? So notice what happened now. I get the log P, and I get a specification that says the non-ionic species, it's gonna be log P of 0.91, which means it's almost 10 times more soluble in a hydrophobic environment than in a watery environment. And we have the log P for the ionic species. That is, when this molecule has a charge, when that nitrogen is protonated, we get a log P of minus 1.6, which roughly means it's about 15 times more soluble in water than in an organic solvent. Now, this might seem trivial right here and right now, almost like a chemistry class, but this property could make the difference between a drug that works versus one that doesn't. but something that has to be injected versus something that you can eat through a pill. Just the solubility might make the whole difference on how it works. So these calculations or these experiments, when they are available, are very, very important. Ah, it crashed again. Has it crashed on your computer? It's only my Mac? That's kind of sad. So, well, wait a second while I open it again. Okay, so back to name to structure, Tylenol. Here we are. Oops. Another value that we can calculate here, as you already saw, or likely saw, is the protonation, the pKa. If we didn't know it, if it was not available, with this molecule on the screen, we can select pKa, and following the same default as presented by the computer, you can click on OK, skip the license, and we should get a graph like this one. Go to calculations, pKa. Well, sorry, calculations, protonation, pKa. No problem. Yeah, leave the default values, click OK on the license, and you should get this. And what you are seeing here is something actually quite useful, quite cool. I really like it a lot. And it's this. A graph of how the populations of the compound are distributed. What we see in this scale is 100% of the concentration on the y-axis. And on the pH axis, what we get is quite literally the pH. Have you ever seen a graph like that before? Maybe biochemistry should be taught like that, but not always. And what we have here is a representation of the molecule with the charge, or the pKa, where it's going to be located. So according to this representation, the pKa for this molecule actually comes from this hydroxyl group. If you take Tylenol to a pH near 10, this hydroxyl group should deprotonate, according to this calculation. What we see over there is, if you click on number 1, and I think they should be ordered in the same way, number 1 is the neutral molecule. This one is the one that should be more soluble in a hydrophobic environment. And this orange graph gets illuminated, and what it's telling us is, in the range between 0 to about pH 9, that is the dominant species. If you click on number 2, it tells us now that the negatively charged species becomes dominant slightly above 9.6 and beyond. The protonation state change and the charge too. If you tell me what's the pH of your stomach? So let's say it's 1.6. What is the dominant species here? What about if this was in the bloodstream at pH 7 or 7.2? Which is the dominant? Still 1. Is there a part of your body that is at pH 10?
No.
I don't think so. But if there was such a thing, that would be 77%, then the deprotonated, the negatively charged one.
Quiero pensar en un lugar súper fácil.
For sure, for example, I don't remember the compound in ranitidine. That's an ATPase inhibitor, isn't it? omeprazole is something that should work in the stomach but not anywhere else. Should we see it? Okay, well, let's finish the exercise, because one thing that it's here that nobody has asked about is this third species. What is that? Where does it exist? Do you see a third graph there? Well, technically it's there. It turns out that there's a possibility of this species that maybe appears a little bit over here. But it's very, very unusual. It requires very extreme conditions that are likely not going to happen in anybody's body. Okay, so I'm gonna close it and cross my fingers that it doesn't crash. Okay, it didn't. And usually, there's several ways to erase things on the screen. The easiest will be just to press no, there's a clean something over here. But usually, what I do is click on this selection tool, select everything, and then click the eraser. Ideally, or in some instances, you can select atoms or bonds or specific things, and you can erase those one at a time. Okay, so structure, name to structure. How do we spell omeprazole?
Well, that's the name of the...
Wow, yeah, it's bigger. Well, I wouldn't recognize it if it's right or wrong. It kind of looks familiar. And there's many parts of this that can change protonation state, right? The nitrogens, and some of these will even affect the aromaticity of those rings. So what do we check first? Should we check the log P or the pKa? The pKa? Okay, let's do the pKa. So, calculations, protonation, pKa. Well, let's find out how weird is that. Okay, nice. So at least at a glance, there's gonna be 4 species, and the 4 of them are gonna be present at any given pH, significantly so. pH for life tell us that this is the orange that is gonna be the most prevalent at neutral pH. pH 7, what is the range? Will be here and here, right? And it's number 1. Click on that.
Number 1?
Yeah. So number 1, which is, according to that, the neutral molecule, between pH 4.8 and pH 9.2, it's going to be the major species. So that's the one that is not going to exist in the stomach, right? If it reaches the bloodstream, yes. But shouldn't, right? It shouldn't. So how do we select one for a lower pH? The green one and the purple, right? So the green one says that between pH 1.4 and 4, this species with an extra proton in this ring should be the most dominant. Well, again, between 1.4 and slightly below that, we have that species where 2 nitrogens are protonated, so a positive charge of 2 will be the dominant between 0 and 1.4. So if you are suffering because your ATPase is pumping too many protons into your stomach, you are going to get one of those 2 species, which are going to be terribly soluble and likely going to interact with the, what type of ATPase is in the stomach? The P-ATPase, I think, and blocking it. And if it reaches the bloodstream, it's going to be poorly soluble, right? At neutral pH, it's not going to be charged, so it's going to be very poorly soluble. And we can compare that. Now that we know this, and I think I have to close it to get back to the other screen. So does anybody have any question about this? You sure? I think you can save this data, these columns of data over here, and plot these in whatever program you want. And you can save everything as an image in case you wanted to use this as data for something else. I'm not, well, I should do it. Save chart as image. Omeprazole. It's gonna be saved as a PNG, which is probably cool enough. If you put it on social media, hashtag omeprazole. So this species will be the most important at neutral pH. If we try to calculate the log P, we are expecting it to be we're expecting it to
Ya me acordé.
seriously? It has a letter too. Log P is 2.45, which means it's more than 100 times more soluble in something hydrophobic than in water. So which one is going to be the most available in the stomach? The charged one, and it's going to be more soluble. If it was to reach the bloodstream, it's going to be a so-so chemical because it's not that soluble. Now this was created by accident, right? But ideally we would like to design drugs like that they are very soluble in the target location but not elsewhere. Let's compare. I'm gonna close it and it's gonna crash, right? So be patient with me. You close your window and go ahead and change the charges on the nitrogens. Oh, look at that. On these nitrogens down here, on this ring and on this one. Click on them, change the charge to +1 on both, and calculate the log P again, which now it's gonna give us a log D, and we are gonna be able to compare how much more soluble in water or in a very water-like solvent versus.
El pK, ¿verdad?
Sí, crashó.
Say that again.
We change the charge.
+1. Nitrogen is gotta be +1.
Sí, sí, crashó.
And then we just do the pKa again.
The log P.
Okay. Porque sigue teniendo seleccionado el porque no tienes que seleccionar.
Yeah, remember, if you select the nitrogen, to change the charge, you need to deselect it. Otherwise, it's going to tell you that it doesn't know how to calculate those properties for fragments. It should look like this. Log P, log P. Remember, protonation pKa is going to give us the curves. Partitioning log P is going to give us the solubility or the partition coefficient. And we should at least get two values, the one for the neutral species, which we already know, and the one for the ionic species. And that's what we get there. The ionic species only became about an order of magnitude more soluble. Oh, sorry. It's about 15 times more soluble in water than in a non-polar solvent, whereas the non-ionic, the one we already tested before, is about 100 times more soluble in something that is not water. So those two protonation states, or the two charges, change between 2 and 1, 3 orders of magnitude, the ability of this compound to solubilize in different environments. So it's pretty dramatic, right? 1,000 times at the least. If we were to use our calculators and get the antilog, we could actually get the real number for these differences. I always keep losing track of time when I'm with you guys. So what's the purpose of these tools? This graphical interaction through Sketch, I like a lot because it's easy to teach with and it's fairly easy to use again. Now, it becomes really difficult to use when you want to perform these calculations over thousands of compounds. And next class, unless there's any questions that you bring up for next class, we're going to take a look at another database that it's also fairly complete, but more often than not misses this data. So if you are working with that information that is not available in drug bank, not available in PubChem, sometimes you have to do it yourself. That is the moral of the story. Any questions? No? Okay, so I focus on drugs. Shouldn't we test this on something that is a metabolite? Just to get an idea of how complex metabolites can be. Well, in fact, this is something that I will have liked to try it and do it on a biochemistry class, but because we don't usually have classrooms as big for biochemistry in terms of the computer space, it's kind of difficult. So now this time go in name to structure and please type L-histidine. What do you mean was? Has never been.
L what?
Histidine, an amino acid.
Yeah, I'm
Don't you remember how tough was it to figure out the amphotericity of that molecule? And how could it have a charge that was neutral, a minus, a plus? Well, that is actually fairly easy to visualize here. Here we have L-histidine, that is the form that is prevalent in organic life. What should we do first, protonation or pKa? pKa, right? Because this is the complex molecule. And it doesn't crash when I do this. So. So here we go. Now, when I see this graph, I can understand why it's hard to teach what happens to histidine at different pHs. So let's start in the simplest, at least from the point of view of organic life, the simplest pH.
Blue one.
The blue one that is pretty much centered around pH 7.6 or 8. So if you click on the blue one, which is number 3, you get that distribution from 6.6 to 9.4. Notice that this 6.6 value corresponds to the pKa of this. It's assigned to the nitrogen of the backbone of this amino acid. It's telling us, because of these two charges, a positive and a negative, that is the Switzer ion. It's a molecule that has two charges, but because they are opposite, the molecule itself is neutral. Okay? That is the Switzer ion that we talk about in biochemistry that was difficult to figure out what it meant. What should happen at a lower pH? Well, at a lower pH we have more protons. So the acid on these amino acids should capture them. So if you click on the violet molecule at pH below 6, between 1.8 and 6, the ring is protonated. The pKa of the ring is high enough that it traps a proton, and now the Switzer ion that was neutral becomes positively charged. We're still dealing with L-histidine. It hasn't changed at all other than the protonation state. And neutral pH is going to be a Switzer ion like any other amino acid. At a slightly acidic pH, it becomes a positively charged amino acid. And if we go all the way to, what color is this? Deep purple? Excuse the pun. The acid becomes neutralized. The charge becomes +2. But this can only exist below pH 1.8. So, did I exceed the time of the class? I'm sorry. But I love to do this. Then, if you remove protons, if we go to number 1, above pH 9, which shouldn't occur in your bodies, we lose one proton from the nitrogen, and this becomes a negative molecule, a -1 molecule. And still, for more extreme pHs, number 4, the negative charge of the acid is there, but also this nitrogen can lose a proton. Well above pH 13, which I think nobody here has ever prepared a solution of pH 13, right? But it could happen. And still there's another species that was way down there. Where are you? This one. This is an isomer. Yeah, it's very... You can see that this one barely peaks near the one that it's the Switzer ion. Just a similar isomer. There's another species of histidine where this carbon can lose a proton. And this program cannot predict it, but it can happen in certain environments in proteins. Has been measured by NMR, but because a carbon shouldn't gain or lose protons, it's not predicted by these calculations, by these models. So, does it make now a little bit more sense what happens with histidine? That it starts being a positively charged molecule, becomes neutral, and then becomes negative? Well, I hope it does. Which one is going to be more soluble? Any of the charged ones, right? Either the one that exists here with a positive charge, or the one that exists way over here at pH 9.4. And the one down here, that Switzer ion, it's going to have mixed properties. It's going to be, depending on the type of molecule, might be less soluble once it's neutral and slightly more soluble. The amphoteric molecules do that. They are weird because of that, because they are charged. They are really charged. They are not neutral. They just behave as neutral molecules, but they are really charged. And just to emphasize that point, I'm going to click again on, where is my blue one? +1, -1. It's neutral, but it's really charged. So it's going to interact nicely with water in those places. Okay, now that is about it. Any questions? No? Should we look at other drugs? Well, tell you what. We have just 1 minute. So let's go for a vitamin. One of the so-called liposoluble vitamins. Do you remember anyone?
E.
What? E? Just E like that? Let's pick, well, okay, so
B12.
B12? Let's see if we can get it with that name. I don't know, actually. I don't memorize those things. So, can you spell that for me? CO? Like B as in boat? Donkey, B? Like that? COBALMINE? Without E, thank you. And wow! Does that look ugly or what?
Yes.
Why does it look ugly? Well, because the program is doing its best to represent a molecule that should be viewed as three-dimensional in a flat format.
Así está el cubano.
Yeah. Let's see if we can actually calculate a pKa. Maybe because of the metal, this won't work. But there's only one way to find out, right?
Try.
Do or do not try it. Come on,
I know.
Rodolfo.
I know.
You're going back to Dagoba.
I know.
¿Te acuerdas que yo apuñalé mi...
Hey, don't confess to crimes here. I'm bound by my ethics to report you. So yeah, actually it does, but where are my species? I guess it's kind of complicated for the program to try to represent it in a tiny window.
Está abajito.
Yeah? Well, down where? You mean you can see them, but I cannot.
Yeah, that one.
Yeah, but difficult to read. Can you see in yours the range of charges? It starts in -5 all the way to 4, to +4. Why? You just have to look at the structure. It has plenty of nitrogens and oxygens right next to one another. And if that wasn't enough, there's a phosphate. And a phosphate, even it's in a phosphodiester, actually in 2 phosphodiester bonds, at least it has one oxygen that can gain and lose a proton. it's been argued if evolution actually selected these molecules because they are always going to be soluble and going to be able to interact with everything in the cell or in the bloodstream or in the body. And of course, cobalamin was not the right liposoluble vitamin because just because of these charges, it's always going to be soluble. So next class, I'll bring another example of something that is not going to be as soluble. Retinol, retinoic acid are going to be so soluble, but not as much. Okay, guys, any questions? No? Then at least on my part, you are free to go and have a nice weekend.
Adoro.